Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back, dear friends. Today we will solve this problem by using a new method, that is virtual work method, for finding deflection and slope. So statement is given that for the loading shown, find out the deflection at point A and slope at free end, that is at point A. So we have to find deflection at point A, which is YA, and slope at free end, which is also slope at point A, by using virtual work method. So in this method, what we are going to do is that this is the real system. This is real system, and we will create a virtual system, and we will put a unit load at this point A, because we are interested to find out the deflection at this point and slope. So for deflection you will put a unit load on point A, and for finding the slope you will have to put a unit couple at point A, and at the end you will be able to pick what I am saying now. So let's start with the solution. So basically, if you see this beam is a beam of length L acted upon by uniformly increasing load W0. Clear? So you can see there is only load W0 acting on these beams, and there is no other load acting on this beam. So we will take the beam of length L having limits x is equal to 0 and x is equal to L. So what we will do is, first we will find the moment equation, because by using virtual work method we have deflection which is equal to y, or we can also represent it as delta, and this delta is equal to integral of m into mv divided by EI here into dx, while this slope is equal to also integral of m into mv into dx divided by EI. Now here the limit starts from 0 to L. Clear? So we will put 0 to L, because there is no other load, so it will act as a unit length, or limit will be from 0 to L. Now what is M? M is the bending moment for the real system, and MV is the bending moment for the virtual system. So we will first calculate the bending moment for actual, and then bending moment for the virtual system, and then we will put the value in order to calculate this deflection as well as slope. So for this system, which is real one, so you can see this load is W0 and it is acting at a length of L. Clear? So if we cut this beam at this position, clear? So what I have to do is I have to draw a free body diagram of this beam. Clear? So this is point A, and here the load will be like this one. So you can see the load will be like this, and let this distance is x. Clear? This distance is x. When we cut the beam over here, definitely there will be a shear force V and a reaction moment M, and let this point is point J. Clear? So we are interested to find out the moment of this cut section. Okay. So let proceed. You can see here this W0 is for whole length L. So here this W will be x W into x, or W0 into x over L, because it is acting on x length of the whole beam. So this load will be W0 into x over L. So we will apply moment equation. Sum of all moment about point J is equal to 0, and counterclockwise is taken as positive. So you can see at point J there is a moment M acting, which is reaction moment, and this moment will be positive because it is counterclockwise rotation. And due to this uniformly increasing load, there will be a moment. So if I present this uniformly distributed load like into concentrated load, so this was total length x, so it will be acting at a distance of x by 3. Clear? We have already discussed it. And to convert this uniformly increasing load into concentrated load, so this load, as this is a triangular area, so this load will be equal to 1 over 2 W naught into x over L into this distance, which is x. So it will be x. So this, due to this load, concentrated load, there will be a moment, and that will be at about this point J. It will be also a positive because it is counterclockwise. So the positive, this concentrated load is equal to 1 over 2 W naught x square, clear, over L into perpendicular distance is 1 by x by 3. So their sum must be equal to 0. So implies that we get the moment is equal to minus this 3 to 6, 6L minus 1 over 6L into W naught x cube. So this will be the moment for this real system. Okay. Now what we have to do, we have to find this moment for the virtual system. So what you have to do is that you have to draw this beam, clear. So this is simply supported beam. So at this is point A, clear, and there is a support at the end. So at point A you will, because you are interested to find out the deflection at point A, so here you will apply a unit load, and this is total length L, clear. So for this, if you cut the beam over here at section 1-1, clear, so we will draw the free bar diagram. So at section 1-1, this is moment A, there is a unit load, that is 1. When you cut the beam at section 1-1, there will be a shear force and reaction moment, and let this distance is x, clear. So what we have to do is that we will apply the moment equation, that sum of all moment about this section 1-1 should be equal to 0, taking the counterclockwise as positive. So you can see there is a moment M that is positive because it's counterclockwise, and due to this unit load, it produce again a counterclockwise movement, and that will be equal to this load multiplied by this perpendicular distance, and that will be equal to plus 1 into x. Their sum must be equal to 0. It means that this movement will be equal to minus x. Now this movement is virtual movement, and I will write V over here. Now it is clear, mv. Now you have actual movement and as well as virtual movement. So I will draw a table in order to fully explain it. So let this A beam is AB, and the boundaries are that x start from 0, x is greater or equal to 0 and less or equal to L, and we have this actual movement and we have this virtual movement. Okay, so you can put the actual movement is minus 1 over 6L W naught into x cube, and this virtual movement is minus x. Again here we are first finding deflection, so it's only for deflection. For slope you have to give the movement, unit movement at this point, clear. When we will move further, you will clearly understand it. Okay, now we will apply this equation. This is the main equation. So we will apply equation deflection at A is equal to delta, and this delta is equal to, or you can also use YA, so 0 to L, and it is M into MV divided by EI into dx. So you have the value of M and MV, you can put it as 1 over E is constant, so I will take it out, so 1 over E into I, and it will be integral of M into MV. Now M is minus 1 over 6 L W naught X cube, clear, and this MV is minus X into dx. So when you multiply it, and the limit will be from 0 to L, so it will be 1 over EI, clear, and it will be integral from 0 to L, and this will be equal to minus W naught X4, and minus minus will be plus, so W naught X4 over 6L. Okay, into dx. If you further simplify it, W naught is constant, 6 and L is constant, so you can take it out as well. So W naught over 6EI into L, and integral of 0 to L, and it will be X4 into dx. So it will be W naught over 6EI into L, and this will be integral of X4, which will be X5 over 5. And the limit will be from 0 to L. So if you put the limit, so it will be W naught L5 over 30 EI into L. Clear? So this delta or deflection at point A will be equal to W naught L4 over 30 EI. So this is the deflection at point A. You can see this is deflection at point A. Now here the deflection, this is simply cantilever beam, so deflection will be downward. So here this value comes out to be positive, so it means that our assumption was of showing the force was wrong. So you can see that this will be a downward deflection. Clear? So this is the value of deflection. Now we will move toward the, for finding the slope at point A. So slope at point A or free end. So for that you have to take the same beam, cantilever beam, clear. The one end is fixed, total length is L. Now here at point A you have to give the unit movement, the value of unit movement here, and again you will have to find MV. So if we cut this section at 1 1, so this will be like, this will be a unit movement that is given. There will be a shear force and a virtual movement reaction, and let this distance is x. So we will apply sum of all movement about 1-1 is equal to 0, taking counterclockwise is positive. So you can see here this movement is positive, clear, MV, and this movement is negative, clear. So it is 1, so it will be minus 1 is equal to 0. So MV is equal to 1, clear. Again the value of this moment is 1, clear, and we have seen that MV is counterclockwise and it is positive, so MV is equal to 1. Now you, for finding the slope at point A, you have integral of 0 to L M into MV divided by EI into dx. So again you have to put the values, 1 over E is taken out as these are constant, so 1 over EI integral of 0 to L, and m is again the same because this real movement will be same one. Clear? So it is minus 1 over 6 L W naught into x cube, and this moment is now mv is 1. So when you multiply these two, so it will be 1 over ei into integral of minus w naught x cube over 6L into dx, and limit will be from 0 to L. So again, deflection at point A is equal to W naught 6L. These are constants, so we will take them out. So W naught over 6L into EI, and we will only have integral of 0 to L, and it will be x cube into dx. So minus W naught over 6EI into L, and this will be x4 over 4, and the limit will be from 0 to L. So when you put the limit, so it will be W naught L4 over 24 EI into L. So deflection at point A will be equal to minus W naught into L cube over 24 EI. So you can see that deflection is negative. So negative means clockwise. So here you can see that if you have a beam, cantilever beam that is acted upon by uniformly increasing load, so definitely it will bend like this. Clear? So this slope, this is the axis of the, so this slope theta A, so this is counterclockwise. You can see this is counterclockwise. So again here we have a negative sign, which means clockwise direction. So our assumption that was our assumption in choosing the direction of force was wrong. So we can say that this theta A will be equal to W naught L cube over 24 EI, and this will be a counterclockwise direction. So this was all about virtual work method for finding deflection and slope. I hope you have enjoyed, and in our next problem we will solve a bit complex problem based on virtual work method for deflection and slope. So stay tuned to my channel and keep watching the videos. Thank you.